Hey guys, welcome back to another video. In the last video, we talked about Coulomb's law. So we talked about the force on charges, point charges. And in this video, we're going to be talking about something very similar and is closely related to the force, electric force. And it is electric field strength. What is electric field strength? It is basically measured in terms of force as well, and it is very similar to force. How's it similar? So if I go through the definition, notice electric field strength expressed as E is basically the electric force per unit positive charge. Okay, so electric field is basically the electric force, the one that both, oh my god, okay, the one that both the charges Q1 or Q2 or Q3, whatever, fields experiences by being in the vicinity of each other's charge, electric field. Right, so it is the electric force that is caused by the electric fields. It is that force per unit positive charge. So we always think of the field lines in terms of positive charge. If you remember in the last video, in the last video, we were talking about field lines, right? And I told you that we bring in a positive charge to determine the field lines. I don't know if I mentioned the entire thing, but I'll mention the entire thing in this video. So to figure out the field line or any sort of direction in electricity or electric fields, we're going to be considering a positive point charge almost always, and that is seen as the convention because in conventional current it moves from the positive side to negative side, and again in this case as well we're going to be thinking from the aspect of a positive charge. How do we do that? I've already given this example that if you bring two positive charges together, if you're talking about this field line of this positive charge, what you do is you bring a positive charge and see in which direction the force is felt. So for this positive charge, what's going to happen is it's going to be repelled. So the field lines are going to be outwards. When you bring a positive charge near a negative charge, what's going to happen is it's going to be attracted. So this positive charge is going to be attracted. So the field lines are inwards. So we are always thinking from the aspect of a positive charge. So if you're ever confused about the field lines, you can always introduce a positive charge and see in which direction the field lines are going to be. Okay. So what was I talking about? So yeah, right. Electric force per unit positive charge. You have to mention it, right? Okay. So that is your electric field strength. It is nothing but the force felt per unit charge. So if it is the force that will be felt by 1 coulomb of charge. So if 100 newtons is felt by 10 coulombs, then 10 newton of force will be felt by 1 coulomb of positive charge. That is basically your electric field strength. Okay. So by definition, you can formulate the formula, which is E, electric field strength, is force per unit charge. Okay. Right. In this case, I have to clarify the notation, the 1 and 2 part, YE1 and YQ2. So in this case, we are going to take the electric field of one charge, let's say Q1, it is its electric field line, electric field E, right? So the field around Q1 is being denoted as E1, electric field strength, and we're going to be measuring Q1's electric field strength. So to measure the electric field strength of Q1, what do? We keep the electric field of Q1 and introduce a test positive charge. This is your test positive charge. Using this, you're going to test the electric field strength of Q1 of Q1. How do you do that? So you bring in the Q2 charged particle and you bring it in the vicinity of Q1. Now what you do? You then find the force that this feels. In this case, it's going to be a repulsive force, so outwards. And you find that force, plug it in, and then you plug in this charge, the charge of the test particle. So if Q2 is 5 coulombs and the force felt is 10 divided by 5, 2. 2 is the electric field strength in this position. Electric field strength in this position of Q1. So if you now have to find out the electric field strength of Q2, what would you do? The exact opposite. What is it? You would write E2 of this point charge, the electric field of Q2, and equals to the force. It's going to remain the same. So you can write it as F, because F1 and F2 is the same thing. I talked about this in the first video. Right, so E2 is equals to force. Now, which charge do you take? Take the charge Q1. This is now the test charge, because you're testing the electric field of Q2. Yeah, Q2, which is E2, the electric field strength of Q2, right? So you divide the force felt by Q1, and you're going to include the force include the charge Q1, because this is the test charge. You want to figure out what is the field strength in this position right now due to this charge. So you're finding the force felt by Q1 in this position due to this charge. So you're dividing the force by the charge on Q1. That is it. That is how you find electric field strength. Force felt by either of the charge divided by the charge of the test charge that is brought inside the electric field. Okay. So that is how you find the electric field strength. That's the basic formula. That is the basic formula according to the definition. Right. So this is what I've talked about in this. Now, how do you get to the more specific formula for spherical or point charges? Remember, right now we're not talking about uniform field lines. We're talking about point charges. And point charges, mind you, has radial fields. What does radial field mean? These are not uniform. What does that mean? The electric field strength as you go away from the charge is going to decrease. So it's not constant. When would it be constant? So if, let's say, this was a plate, charged plate, in this case, the electric field would be uniform, meaning the electric field strength at any position would be equal. But in this case, we're talking about, notice, we're talking about point charges. They have radial fields, meaning these arrows are, see, moving away from each other. So the strength at this position, electric field strength at this position is less than electric field strength in that position, right? So if you understand that, good. So that is why we need to figure out a different formula or a more specific formula for point charges. How do we do that? Very simple. If you remember force, the formula for force in the last video, Coulomb's law, what was the formula? The formula was force is equals to K, the constant, Q1 times Q2 divided by R square. This is your entire force. And this is same for both the charges. So you simply plug that in over here instead of the force. And you keep Q2 as it is, the test charge that is brought under the electric field. Great. So if you divide both, you're going to notice that the charges cancel out. And you're left with K, the constant, Q1 divided by R square. Notice, now you don't even need another test charge to determine the electric field strength. So if you have a random charge lying around, you can find out its electric field strength at different position. In this position, it's going to be different. In this position, it's going to be different. In this position, it's going to be different. How do you figure out? You need the constant, which is always the same. Depending on the material, it's going to have different permittivity values. But for our syllabus, it's always going to be the same. Always consider it vacuum and E naught. So constant is basically the same for our syllabus, for our question papers, right? Okay, so again, the constant remains the same. You plug in the charge of Q1 that you're testing. Let's say 5 coulomb, you plug in 5 coulomb. And R square, what is R square? The distance from the center of the charge to a random point where you want to measure out the electric field strength. So at position A, this is the radius or separation. At position B, this is the separation. And like that, you're going to find the separation and square that value and divide KQ1 by R square. Simple. What is the unit of electric field strength, by the way? It is Newton per Coulomb, as mentioned over here, Newton per Coulomb, N by C. There is also another unit for this. You can figure it out using base SI units, but this is going to be covered in another chapter when we learn about electric potential. So after learning electric potential, I'm going to tell you how this unit is derived and why it's useful. Right, for now, you basically write the unit as N per Coulomb. Great. So, right, okay. So this is your electric field strength for point charges. Okay, great. How electric field lines express electric field strength? Okay, I was just talking about, radial field lines, right? And I was giving you an example. If let's say this positive charge and you have the lines like this, at which position is the field strength the greatest? I'm asking you, at A or B? At which position is the electric field strength the strongest? And why? So if you had to answer it to me, how I would expect the answer is, since at position A, the field lines are closer together, as you can see, the field lines are closer together, therefore, the field strength at that position is stronger. Conversely, at position B, what's happening is the field lines are further apart. That's why the electric field strength at position B is weaker. Okay, so you basically use that logic over here as well for uniform fields where you have charge plates and the field lines are going to express your strength, electric field strength. So if let's say the charge distribution is not uniform and you don't have, let's say, conductive material, or you have an insulator and the charge distribution on it is random. So in that case, what's going to happen, let's say, this is not the right demonstration, wait. Okay, so let's say the charge distribution is very non-uniform. In that case, you're going to see at certain position, the field lines are closer together, and at other points, the field lines are further apart. And what that's going to demonstrate is, over at A, your field strength is weaker compared to over at B, where the field lines are closer and the field strength is greater. Okay, so for field lines of positive and negative charges, how do you express it? Always, the field lines are going to be escaping the positive charge, get away from me, and it's going to enter the negative charge. So, away from positive, enter negative. And you're going to express the diagram just like this. It's the simplest thing ever. Out of the positive charge, enter the negative charge. And you can, don't just leave it at, this. Don't just leave it at this. You need to show these hair follicles as well. So just, show a few field lines that is escaping or entering the charges, and don't complete this cycle, and just fill all the, the entire circumference of the sphere, right? So yeah, this is very simple. And okay, that's, I guess, all about electric field strength. And next we're going to be talking about electric potential energy. All right, next video for that.